So as we begin to talk about waves, we'll want to talk about how we know that waves are a motion of a disturbance. So, if you have a pool and you jump into the pool, right, there's going to be a disturbance and the waves are going to travel out from there. This works with earthquakes as well. You have a disturbance underneath the ground and the shock wave goes throughout, the ground to wherever, however far it goes until it all dampens out. Now, also with waves, it's important to remember the types of waves. So transverse waves are where the particles move perpendicular to the wave motion. So here's a wave, and let's say, the boat's on the water, and the wave, let's say, is going from left to right. The boat's going to move up and down. Now, it turns out ocean waves are a little bit different. They're surface waves, but they're similar in terms of, the medium does move up and down, as in a transverse wave. The crest is the highest point, the trough is the lowest point, and we get the wavelength for any two corresponding places on a wave, a crest to a crest, trough to a trough, or even, here where you go through a trough and then a crest, and then you end up here, you have a full wavelength. Now, longitudinal waves are where the particles move parallel to the wave motion. So let's look at a slinky here. Let's say we have a piece of tape. The wave's moving from left to right, so this is going to be moving back and forth. And that's what we see with longitudinal waves. Crests are compressions, and then the troughs are the stretched regions. And when we studied sound, the compressions were the crest, and then the troughs were the rarefactions. That's where the low pressure was. And yeah, so it's important to know the types of waves. Also, it's important to know how to get the speed of a wave, and this is right off your equation sheet, V equals frequency times wavelength. And so that's pretty straightforward there. And so yeah, let's practice this one as we get started. So you can go ahead and pause the clip. I also want to say this to you. We know that 1 over the period is frequency, and then period is 1 over the frequency. So 1 over period is frequency, and then the period is 1 over frequency. So these are helpful too if you need to be able to go back and forth, which you need to in this one because it says that it takes 10 seconds for each wave. So you're going to need to find the frequency here so you can calculate the speed of the wave. So go ahead and pause the clip and do this one, and when you're ready to check, you can hit play. All right, so we should get 2 meters per second for this wave. 0.1 hertz is the frequency. All right, once you try this one as well, the speed of the wave is 14 meters per second. The distance between the waves are 42 meters, and we want to find the frequency and the period. So go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play. All right, so we should get 0.33 hertz for this, and therefore the period is 3 seconds. So it would take 3 seconds for each corresponding wave to come by. Reflection is important as well, and when you have a wave that hits a fixed end like this, it inverts phase. We did this with that long slinky or long spring. And then an open end is where it will reflect and be the same phase. And so that's where this one is free end, and it's free to go up and down, and we'll send the wave back the same. Now, constructive interference happens where we have two waves coming at each other, and they're on the same side. And so two crests or two troughs, and let's say that this was a meter high, and this is a half a meter high. Well, you just add up the two, and then you would get 1.5 meters for that. Now, another thing to remember is that after they interfere, they continue like nothing happened. They pass through each other, and then they continue like nothing happened. Here's another example here, just moving from top down, giving an example of interference, and then in the middle they're interfered, and then afterwards they continue like nothing happened. Now, destructive interference is where they're on opposite sides. The amplitudes are on opposite sides. We have the displacements on opposite sides. Let's say that this was a meter and this was half a meter. Well, when they interfere, this is, on the negative side, so the resultant would be 0.5 meters here. And then afterwards, they continue like nothing happened. Now, in this one here, with an electromagnetic wave, this is where they're actually perpendicular to each other. You have an electric field and a magnetic field that are perpendicular to each other. This is the X, Y, and Z axis. So the magnetic field is actually out of the page, into the page, out of the page, into the page, and then flat against the page here is the electric field. And they are transverse waves, and they are perpendicular to each other. Now, another thing that we talked about that's important is nothing can go faster than the speed of light. C is the cosmic speed limit. If you even think about the particles in the Large Hadron Collider as they're flying around, they can get very close to the speed of light, but once you get close to the speed of light, you run up against a limit there, because it would actually take an infinite amount of energy, according to Einstein's theories of relativity, to have something go the speed of light, and so that is the speed limit. Okay, so why don't you use your equation sheet, see if you can figure out how to solve this one here. This is a radio wave, 15-meter long electromagnetic radio wave, and we want to find out the frequency of it. So on your equation sheet, you should be able to find out the speed of an electromagnetic wave, assuming a vacuum, or normal air is very close. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play. All right, so we should get 2 times 10 to the 7th hertz as the frequency of this wave. And again, using the speed of light, 3 times 10 to the 8th, and then v equals frequency times wavelength, so speed of light, and then 15 meters is the wavelength. And so remember, radio waves are from a length of 15 meter, or a length of about a water bottle, to the size of the diameter of the Earth. They can be very, very large. Let's try this one here. What's the wavelength of a 6,000 megahertz electromagnetic wave? So in this one, you're going to need to convert to hertz, and then you can figure out the wavelength. So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play. Okay, so we should get megahertz 10 to the 6th. So 6 times 10 to the 9th hertz. And then, therefore, we can find the wavelength is 0.05 meters. So looking about X-ray range there. I'm sorry, microwaves. All right, so now what I want you to do is to try it out to write the full EM spectrum from longest wavelength to shortest in order, starting with radio waves, and then also write out the visible colors of the visible spectrum. And then, so that's first, do that first. And then secondly, what I want you to do is circle the one that has the highest energy, and then circle the one that has the highest frequency. So yeah, go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play. All right, so radio waves, microwaves, infrared, Roy G. Biv, ultraviolet, and then X-ray, and then gamma ray. Gamma ray has the highest frequency and highest energy. Frequency and energy go together. In the visible colors, violet has the highest frequency, highest energy. Forgot the E there. V-I-O-L-E-T, yeah, sorry. And then, so you need to be able to know those by heart, going left to right, and then again, the longest wavelengths to the shortest wavelength. So gamma has the smallest wavelength, highest frequency, highest energy, and then out of visible colors, red has the longest wavelength, lowest amount of energy, and then violet, highest energy, highest frequency. Now, another thing that we want to look at is index of refraction. You have this on your equation sheet, and N equals C over V. And this is important to remember with how the speed of light in a vacuum compares to the speed of light in a medium, because we know in different mediums the speed of the wave can slow down. And you do have this on your equation sheet. C is the speed of light in a vacuum, which you have on your equation sheet as well. So let's go ahead and try this one here. The index of refraction of a crystal is 2. Find the index of light. Find the speed of light in crystal if the index is 2. So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play. All right, so N is C over V, and we're looking for what that is, and it should be 1.5 times 10 to the 8th meters per second. So that means that the speed of light in a crystal is actually half of what it is in a vacuum.